Let's talk about infinity.
Yeah.
Some people think of infinity as just a placeholder, like a heuristic for this is a sufficiently large number beyond our grasp.
Right.
Okay. Computationalists are fond of that. What do you make of the concept of infinity in physics?
The concept of infinity in physics is really interesting. And let me ask you a question, Curt, because we have, we have classical physics, the laws of fluid mechanics, for example, is a good example of classical system. And then we have quantum mechanics, which replaced it. Now, you have so if you ask about infinity, as you say, you have two possibilities. One is that actually in physics, we know infinity sort of exists as a concept in mathematics, of course it does. But in physics, is infinity, when we use infinity, or conversely 1 over infinity, an infinitesimal, when we use these concepts, do we really mean infinity is absolutely, literally infinitely big, bigger than any finite number? Or is it just a placeholder for a very big number, but we don't particularly care exactly how big it is, but it is a very big number, and the laws of physics don't depend sensitively on that number, and all experiments, it doesn't really matter if that number's like a Google or a Google pleth or something like that. So do you think there's a difference between how infinity is used in classical physics and quantum physics? And if so, how would you see it? Do you think infinity is more of a, as a number of, let's say infinity as a number that's bigger than any finite number, so not a placeholder. Do you think that's more of a concept in classical physics or in quantum physics?
In quantum physics, there are infinite dimensional Hilbert spaces. And then because of that, there's something like the Stone-von Neumann theorem. And that's one of the reasons why why QFT is not so trivial compared to quantum mechanics, because you have the conjugate variables of X and P.
Okay, well, look, I think I agree with your answer, but I think you're making it too complicated. I think you're right with what you say, but let me put it like this. So if we, even at high school, when we learn Newton's laws of motion, they're framed in terms of the calculus. F equals, I'm assuming that's, I'm not even sure today whether high school students do the calculus or not. But anyway, certainly first year at university, let's say force equals mass times acceleration, and acceleration is the second, rate of change of position with respect to time. So we use Newton's calculus, Newton-Leibniz calculus, and the calculus involves, infinitesimal numbers like d by dt. Dt is an infinitesimal number in calculus. So you might think that, infinity or an infinitesimal plays an essential role in classical physics. But, people might think, well, in quantum physics, it's all about discrete jumps, everything is discrete jumps of energy. And therefore, it's all somehow finite. Everything is finite. But actually, it's completely the other way around. Because in classical physics, I can take a differential equation, we do this with weather forecasting, of course, where we have partial differential equations that underlie the movement of air, but they're represented on a computer with finite derivatives, so that we don't have like d by dt, we have delta by delta t, and these deltas are finite things. And we know that, at least for short range forecasts, that does pretty well. So there's no kind of essential reason in classical physics why we need to be working with a continuum, the real number continuum. We can just work with discrete numbers and we get answers. If we want to get a slightly more accurate answer, we'll halve the time step or quarter the time step. But you tell me how accurate you want to know it, and I'll tell you the discretization length and the discretization time that will give me an answer to the accuracy you want. But in quantum mechanics, it's completely different, because the basic concept behind a quantum state, sort of you mentioned this effectively, is it's an element of a Hilbert space. And a Hilbert space is a vector space In fact, in quantum mechanics, it's a vector space over the complex numbers. But the point about it being a vector space is that you want to be, or you need to be able to add together two vectors, in other words, two different quantum states, and the resulting addition is itself a quantum state. Mm-hmm. So that's a really important property. Now, if you start discretizing Hilbert space, you will typically lose that property. You'll add together two vectors, and the resulting vector will kind of lie in between two of your points in your discretized space.
Wait, that's not so obvious. So let's see. Let's say you make a grid. Okay, so it's just integer steps.
Make a grid and take a vector. Say you have an origin and you have two vectors which point to two of the points on the grid, and add them together. That the sum of the two is going to split the difference. Unless you've got a grid point which splits the difference, then your vector will no longer be be in the space.
Let's say you have something that's unit 1 in length, and then another that's unit 1 in length, then you get something that's unit 2 in length, but along the same axis. But what's wrong with that?
No, that might work. But if you imagine, if you imagine two, if you discretize, say, a circle, and you imagine two vectors pointing to, let's say, neighboring grid points, and then add together, you're going to split that difference, and your vector will typically then not lie on either.
Okay. So it depends on your discretization.
It will depend on the discretization, but generically, to get these algebraic properties, you need a continuum space. And actually, this I'm not the first to make this point. This was made by Lucian Hardy from Perimeter some years ago, when he came up with what he called reasonable axioms for quantum mechanics. And one is this notion that it's called the continuity notion, that you don't have a space where you can get discrete jumps, even though quantum mechanics is all about discrete jumps. In the so-called unitary phase of quantum evolution, you actually need continuity. It's a critical property. But then the question is, why is it a critical property? And it's only a critical property if you believe that these Hilbert spaces and Hilbert vectors are the fundamental objects of your theory. In other words, if you say, what is the, if I have my theory of quantum physics, what is at the deepest level? Now, in quantum mechanics, at the deepest level is Hilbert space. That doesn't go any deeper than that. That's it. Okay. So then you have to have the continuum of Hilbert space, of Hilbert states rather, to describe quantum mechanics. On the other hand, if you say, well, if you say that, which is sort of what I'm trying to suggest by virtue of this cosmological invariant set postulate, that there may well be something deterministic that underpins quantum physics, then the Hilbert states are not really fundamental. All they're doing is they're the mathematical quantities that you would use when you know that there is some inherent uncertainty in your knowledge of the system, and you want to represent that uncertainty in a kind of statistical way. So Hilbert states, coupled with Born's rule, which is about probabilities of outcomes, then just becomes, if you like, it's not a fundamental property of your theory. It's just something which is useful to use when you want to describe things in a statistical way. And this is actually, again, where p-adic numbers come in, because on a fractal, you can add and multiply using these p-adic numbers, and the result is a p-adic number. So you have this closure under addition and multiplication at this deeper deterministic level. So I have a scheme which leads to a particular type of discretization, which I feel might be a bit too much technically to talk about here, but it exactly has all these properties that you add two vectors and typically the sum doesn't lie, in the discretized space. However, it has this deeper deterministic underpinning. But importantly, it has exactly this property that when you look at the count, if you try and estimate if you try to define the quantum states associated with entangled particles where you do these counterfactual measurements, then to describe the Hilbert states, you will need strictly irrational numbers, either for the amplitudes or the phases of the quantum state. And those are things that are forbidden in the discretization. So this captures precisely this notion of moving off the invariant set, but now it's framed in terms of rational versus irrational numbers in the definition of the Hilbert state. So I think actually that is probably an easier way to, let's say for a practicing quantum theorist to kind of get to the type of model I'm trying to propose here.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for toe mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.